foremost on providing the best possible education. October 21, 2020, yesterday, the Laurentian University Senate voted in favor of delivering the winter 2021 semester via duct remote delivery. The discussion on the question focused first and foremost on providing the best possible education for our students while safeguarding the health, safety, and wellness of students, faculty, and staff. Other factors in the discussion included the advances made in delivering classes via remote learning, the requirements related to hands-on learning, and the overall quality of the student experience. The university will continue to deliver a small number of classes in person, in a similar way to the fall 2020 semester, in which less than 1% of classes were delivered in person. Additionally, the university will continue to welcome students in residence apartments on campus. Staff have been working diligently to implement and maintain COVID-19 protocols to keep students safe and, amidst the circumstances, have created a secure environment for students to live and learn. With recent announcements from the federal government, which welcome international students to Canada, Laurentian is pleased to host students from around the world in compliance with the campus COVID-19 readiness plan. The university continues to support students, faculty, and staff through their day-to-day activities remotely. Laurentian University has been a leader in responding to the COVID-19 pandemic and was the first public university in Canada to recognize the severity of the pandemic, suspending in-person classes in March 2020. The winter semester takes place from January 2021 to April 2021. October 21, 2020, yesterday, the Laurentian University Senate voted in favor of delivering the winter 2021 semester via duct remote delivery. The discussion on the question focused first and foremost on providing the best possible education for our students while safeguarding the health, safety, and wellness of students, faculty, and staff.
All right, good morning, everyone. We should get started. So there's been some chat going on talking about the midterm exam, which of course is 1 week from today. So the exam will be delivered on D2L under the quizzes tab, which I'm pretty sure most of you have probably already experienced by now. So that's where the exam will be. It will be, you will need to have the Respondus lockdown browser on to write the exam. So you have to make sure you do that, get that lockdown installed beforehand. And so the way I have it set up is that the exam will open at 10 a.m. for you to access it on D2L. You need to go on Zoom. No, you won't need to go on Zoom that day. Yeah, so you take the exam on D2L on the quizzes tab. It will open at 10 a.m. And it will close at 11:20. So you'll have an hour and 20 minutes to write it, unless you have an accessibility permission to have a longer time frame. And for the students that have that extra time, I have implemented it, especially for those students, in the time when the quiz will close. Jordan asked about lockdown using our camera. So there's two ways that I can do Respondus, and I have decided not to do the camera version. I'm just doing the browser version. And that's because I'm trusting you guys not to cheat. And I don't know if that's the best idea, but that's what I'm going to do, because I think, I don't know, the whole point is for you to learn some stuff about animal ecology. And if you cheat, well, then you're not going to have learned this stuff. And so that's your loss and not mine, to be blunt. So I'm not using Zoom to watch you as you write. There's 69 of you, so that would just be ludicrous. And I'm also not using the lockdown camera thing, but I am using the browser, and I'm not sure that's even that valuable. It is not an open book test. I've tried to implement a timing restriction to some degree, like the hour and 20 minutes, which will give you less time to look through your lecture notes you may have written down. But anyhow, as I said, it's up to you to learn the content and to understand it. And the test is a way for me to evaluate it. And if you cheat, you cheat. I'm super disappointed, of course, if you cheat. But the onus is on you to be a responsible student. So I'm just going to go with that and hope that you learn some cool stuff. I mean, that's the point, right? Okay. The lockdown browser, it's, if you have not written a test under the quizzes tab of D2L before, you may not have installed lockdown, but it is there in D2L. So you should go in and make sure you have that set up. I have never done it on my end, so I'm not sure what it looks like for you guys to do it. But when I taught animal histology at the end of last semester, all of the students were able to do it through D2L to put Respondus lockdown on their computers. So basically what it does is mean you can't go to anything else on your computer or your tablet besides the test you're writing. So it's supposed to prevent you from going to your PowerPoints and lecture notes and scrolling and checking things on the internet and stuff while you're writing. Okay, so please go into D2L and have a look at getting Respondus lockdown set up on your computer. So that means that when the exam starts, that lockdown will be implemented. Okay, I'm gonna get into the lecture, and then we can talk more about the exam after that. But I want to get into this lecture content because it will be on the exam. So let's do that. So I'm gonna go to my share screen. Oops. First, I need to go to share screen. And today I'm actually going to try something different again. Let me see here. Last time when I gave a lecture, when I needed to use Blackboard, I went to the university and I taught from the teaching lab so I could use the Blackboard. Today, I thought I'd spice it up a little bit, and I'm actually, there's a benefit to having a kid. I've showed you some of my kid stuff before. I have this really cool, little chalkboard. So just to keep things interesting, maybe a little bit silly, I'm going to be trying to use this little Blackboard of my daughter's to try and share some stuff with you, some of the content. Okay, so today we're going to be doing our first lecture on population growth. The lecture on Monday is the second one on population growth. So today we're going to talk about geometric and exponential, and then on Monday we're going to talk about logistic growth. And I know you've learned about these before in Principles of Ecology, but we'll talk about them in some more detail, and we'll actually do some calculations using these growth formulas. Okay. All right, so first, talking about population growth and rates of population increase. So populations, of course, are dynamic, right? They change over time. So depending on the species, the population size, it might actually change from hour to hour, something that reproduces really quickly. It may change from day to day, season to season, or maybe for a longer lived animal, it's going to be year to year variation in population size. So in some years, animals are, super abundant if conditions are great. And in other years, animals might be really rare. So, we talked about metapopulation systems, local populations, those deans, right? Those subpopulations, they can appear and expand and decline. They can wink in and out of existence, right? So populations are dynamic. They're always changing. So these changes come about, of course, because the animals in the population are interacting with their environment. And those interactions are going to affect the birth rates, right? How many are born in a year, the death rates, and also, of course, the movement of individuals, which we again talked about in the spatial dispersion aspect of individuals migrating between areas, but also in individuals immigrating and emigrating between patches of habitat. So, of course, all these things are going to impact population size. So the demographic techniques we talked about, so life tables that we talked about last time, those are really, really useful because they allow us to project future changes in populations. So we can do this fairly precise projections about what's going to happen. And I use the word projection there, not predict, because there's actually a difference. So these formulas that, they allow us to project what could happen in a mathematical sense, but that's not necessarily the same thing as a prediction of what the population is actually going to have happen. I see some chats popping up. I'm just going to see if there are things that I need to address now. Okay. All right. So there's just some info there about respondus. Okay. In the chat. Okay. So, last time we looked at the use of information in life tables to calculate this thing called capital R with a subscript 0, right? We talked about this R. And this is the finite per capita rate of population growth over one generation, if you remember. So this means that there's non-overlapping generations. Okay, so it allows us to project future population, right? But in this sort of discrete way, in this just this one generation way. And we talked also. So remember, we used one of the columns in the life table to be able to calculate R. It was the sum of all the values in that column. And then we talked about T, the generation time, which was the sum of the final data in the column of the life table. So from that life table, we were able to get some of this information about these different variables that relate to population increase. The other thing to mention here is this idea of the mean length of a generation. So it's the mean period of time elapsing between the production or the birth of the parent generation and then the production and birth of their offspring, right? So it's different than thinking about age at maturity. Okay, so if you think about humans, a female human reaches sexual maturity at about 11 or 12 years of age. But the first reproductive event doesn't usually happen, at least in North America, until about maybe 25 or 28 years old, right? So there's this difference between age at maturity and this time period when offspring are produced, right? So when we talk about, again, this R value, this is used for calculating population growth, again, for animals that have these non-overlapping generations. So that means there's only one generation per year, right? We don't have these overlapping generations like humans have, for example. So again, it's this just one generation per year. So we would call that a discrete model. And then we can use the information in life tables to calculate some other rates of population increase. So we're going to talk about those as well. Okay. So for example, if we divide the total number of individuals in a given age class, and if you remember from the life table notation, right, we had the value X was indicating age classes, and that age class can be different depending on the type of animal you're talking about. Something with a very fast life history like fruit flies, it might be measured in days, but in something that lives a long time like elephants, it might be measured in decades, for example. Okay, so if you divide the total number of individuals in age class X plus 1, right? So the total number of individuals in age class X plus 1 by the total number of individuals in the previous age class, you can get a value of lambda. this is called lambda, for each time period, right? So we're just going from one time period to the next. So this gives you this calculated value of lambda, which projects the population growth from one point to the next, right? So lambda projects population growth from one point in time to another. So it's always going to be positive, okay? So again, it's the number of individuals at age class x plus 1 divided by the number of individuals at that the previous age class, x in this case, okay? So that's lambda, projects the population growth from one point in time to another. It's always positive. So in contrast, if you remember that capital R sub 0 value, it can be, if you remember, it can be 1, it can be less than 1, and it can also be greater than 1, right? So that means that R, capital R value, is measuring the finite rate of increase in terms of, again, discrete generation time, right? All right, and so we can also use lambda, this value of population growth, as a multiplier to project, but again, not predict, but project what population size is going to be at some time point in the future. And that's by using this formula. N subscript t equals n subscript 0 lambda to the power of t, okay? So in this case, this capital N sub 0, that value is the initial population size. 0 means at the start, right? So that's the initial population size. The capital N is population size. So initial population size, lambda is what we just said. This is this population growth rate. T is time, right? And NT then, that's the number of individuals or population size at time t. So this calculation, this formula, is the formula for what is called geometric population growth, okay? So geometric population growth is represented by this formula. So this t value that's here, this time, this can be, again, however you define time. So remember, in the life table, we could talk about it. We could talk about it being in weeks or days or years or whatever it might be. Okay, so this t can reflect that the age categories that you actually have in your life table. You could have that to match up. So if we think about the hypothetical life table that we did last time, and you take a look at some of the numbers in that, you can actually apply this lambda calculation to some of those to see what the population growth rate is over that discrete interval. So, for example, from the life table last time, and I'm going to try using my little Blackboard thing to show you this. If you remember, if you look back at your notes when you're working on this, so the N2 value, for example, was 30, and the N1 value from that life table was 50. That was the number of individuals in each of those time periods, right? So if you want to calculate lambda from that, right, and we're doing this, and it would be N2 over N1, right? So it would be 30 over 50, right? And when you calculate that, it's 0.6. So that 0.6 gives you a value of the population growth, the geometric, it gives you an estimate of that sort of discrete population growth from one interval to the next, right? So a very simplistic way to get at a population growth rate that's, again, discrete, okay? That R value, that R naught value, R0 value, it also allows us to calculate another value, little r, right here. This is the per capita rate of increase per unit time, okay? So per capita. So it's a measure of the instantaneous rate of change in population size per individual. So per capita means per individual, right? So it's a measure of this instantaneous rate of population change per individual. So it allows us to calculate population growth rate now when there are overlapping generations, right? So again, this capital R value, that's when there's no overlapping generations, versus this little r value, which allows us to calculate population growth rate over overlapping generations. And there's a way to convert this non-overlapping to an overlapping calculation using the formula that's right here, okay? So in a closed population, this little r value, remember, a closed population means nobody's coming in and out. There's no immigration or emigration. So in a closed population, this R value is called the intrinsic rate of increase, right? That's the available rate of increase for individual there. So again, so this relationship between little r and big R is approximately this. So this per capita rate of increase is equal to the natural log of that capital R value divided by T, that generation time that we talked about. Okay, so we can relate these two to each other. So the per capita rate of increase or decrease can be then converted to a finite rate of increase by this value, by this formula, this calculation, which is lambda is equal to E to the power of R. If you remember E, this is the base of natural logarithms, right? That E value. Okay. So again, we can do this we can go from this finite version to this per capita version by using this relationship. Little r is equal to the natural log of the capital R divided by T, the generation time. So this allows us to convert this non-overlapping to overlapping generation to calculate the per capita rate of population growth. Okay, and then we can convert it to a finite rate with this calculation. Lambda is equal to E, which again is the base of the natural log to the power of R, that per capita rate of increase. Okay, and we're going to come back to some of that stuff, but I want to say a few things just about sort of models in general. So population growth models, so I already made the comment that they allow to project, but not necessarily predict, and there's a subtle difference there. So models of population growth are basically their hypotheses, right, about how populations grow. They're projections about how populations grow. So by presenting population growth in this sort of mathematical way, we can work out those mathematical projections and then see how well our models fit with real data, right? So in making models, there's a trade-off though, right? You can have a really generally applicable model, or you can have a highly accurate specific model. So in terms of general applicability, the models are going to have features, that fit basic sort of patterns, but not details. So they might fit basic patterns of many species, but that's going to be less powerful than if you have a very particular species, say an endangered species that you want to make specific projections about. Then you want to, you sacrifice accuracy by having this general applicability. There's this trade-off. So accurate models for one species, they won't be applicable to other species, but they might get at some really important fine details that you need about a particular species, right? So different models will be good for different species or different situations. And some models might fit many scenarios quite generally, but others are work well, only for very specific scenarios. So there's this variation. And again, models are just hypotheses, right? They're not the reality. In an ideal world, you would make a model and then you'd be able to collect real data and test your model. And it's not always possible to do that. There's two basic types of growth models. So I've already sort of alluded to this. First are the finite models that look at the change in a population over a discrete time interval, right? So these are useful for species for which all the reproduction occurs at once. And most mortality is seasonal over a short time. So this is the case for those non-overlapping generations, right? Everybody is born at once or is hatched at once, and then everybody pretty much dies at the same time over a short time period. So again, this would be non-overlapping generations. So this, geometric growth could be an example of this type of model. And then instantaneous models. So these models look at population change at an instant in time. So it's like a snapshot, but it's a snapshot of a population of animals that birth and die over long time periods that overlap. Okay, so it's a snapshot, but it's useful a model for species that reproduce and die again over long time intervals with lots of overlap in generations. So they allow us to look at long-term population change. We can, examine patterns of like growing or declining populations as opposed to short-term fluctuations, which is what you get at with these finite models, right? So finite models are these short-term fluctuations. That's what you can look at. Instantaneous models give you a snapshot, but they allow you to look at larger patterns of increase and decline over long time periods because they allow for overlap of generations. That is, lots of dying and birthing is happening over overlapping time periods. So, little r, that per capita rate of increase is an example there. And most of the models that we're going to look at are going to be related to these instantaneous models, that growth is relatively long-term, population growth is over long time periods. So we're going to focus on those for our discussion. Before we go too far into more of that, though, let's just go through some of these symbols that I've already shown you some of these, but let's just get into them a little more. So we'll review the meaning of just reemphasize the meaning of some of these. So capital N, of course, is population size. You've seen that before. T, that's time. And again, that can be in different units of measurement, depending on the animal you're working on. And so then NT, this is population size at time T, right? The subscript tells us that it's at time T, okay? This one here, N2 minus N1 divided by T2 minus T1. This is a finite rate of population growth, right? Finite growth rate of the population. When you think about this, so this is population size at time 2 minus the population size at time 1, right? So it's population size difference over the time difference at that same interval, right? So it makes sense that that would be a way to do this finite sort of calculation of the population growth rate. It's basically the change in the population size divided by the change in time, okay? And so then this value, this capital R does not have that little zero subscript, right? This is just capital R, is equal to the population size at time t plus 1 divided by the population size at time t. And this should look sort of familiar. This is basically that life table notation that I just told you about, except in the life table, it was a little n instead of a capital N. And so that in the life table, that's the number of animals we count. In this case, this is a capital N means an estimate of population size, right? So this is an estimate. But basically, we're looking at this same thing again, except that instead of using the recorded values that you have in a life table, now we're applying like an estimated population size, which is what the capital N is referring to, right? So it gives you a similar thing as that lambda calculation does using the life table values, okay? And then little r, which we've said, right, is the instantaneous per capita growth rate. And it can be also figured out by doing a difference between births and deaths, right? So B is the instantaneous birth rate and D is the instantaneous death rate. So the difference between those two, which makes sense, right, is going to be the instantaneous per capita growth rate, the growth rate per individual, okay? So that's that. And then the last one here is this one, dn over dt. And you might recognize this, and don't be frightened, but this is that calculus notation, right? So d means the derivative, if you remember your calculus. So this d isn't d multiplied by n over d multiplied by t. The d means the derivative. So what, if you remember your calculus interpretation, what that means is the change in population size with respect to change in time. So it's very similar to what this is saying, right? So d is just saying, taking the derivative of n with respect to t. But what it means in sort of biological terms is the change in population size with respect to the change in time, okay? So again, it's this instantaneous change of n with respect to the change in time, okay? So again, it's very similar to what's happening here. It's just written in a calculus notation. I think I saw, it's hard to tell when I'm here in this view for me, but looks like there's some chat here. Okay, it's more about the respondus stuff. Okay. All right, we'll come back to that after. Okay, so there's some review of symbols. So now we're going to move into talking about exponential population growth. So exponential growth models, the key thing about these is that they assume that the birth rate and the death rate remain constant over time. That doesn't mean that B and D are the same. That they're equal to each other, but it means that they are constant over time. So there's no change in the birth rate and there's no change in the death rate over time in this population, okay? And here I go to my handy dandy little blackboard again. I stole chalk and an eraser from school, don't tell school. Okay, so again, the key assumption here is that these birth rates and death rates are constant over time, okay? So if that's true, right, if the birth rates and the death rates are constant over time, right, so we're gonna write this out. So dn over dt, okay? I hope you guys can see it. Okay, so that's gonna be basically saying that the population size times the birth rate minus the population size times the death rate, right? So the change in the population is going to be how many individuals times how many are born minus how many individuals times how many are dead, right? So in this case now, we're talking about population size times births minus population size times deaths. That's going to tell us about the instantaneous population growth rate, okay? So then we can simplify this, right, in mathematical notation. So the value that's common to both of these is the n, right, the n value. So you can filter out that n value. So you've got b minus d times n, right? This is just doing simple math, okay? Now, we said that r is equal to b minus d, right? So remember, we said that r is equal to b minus d. So we have that right here. R is equal to b minus d. So then we can say this is r n, right? We're just substituting that in. So now we have dn over dt is equal to r times n, right? Hopefully that all makes sense to everybody. So we substitute that in, that's what we get. Okay, so what this is saying is that the change is directly proportional to the population size, right? So the change is directly proportional to the population size, is what that says. Okay. So then we're saying that R is constant, right? Because births and deaths remain constant. So R is constant since B and D are constant. So then what we can do is solve for R, right? And so to solve for R, we have to divide both sides of the equation by n, right? We want to get rid of this n. So we divide both sides of the equation by n, and then you get the formula that's on your computer screen. R equals dn over n dt, right? So again, we just solve for R, which means we divide both sides of this equation by n, and then you get the equation that's on your screen, which is R is equal to dn over n dt, okay? So the result then of exponential growth is that if the birth rates are greater than the death rates, then R is going to be bigger than 0, right? And so your population is going to increase faster and faster and faster. And that's what's shown on the graph right here, okay? So when you look at population size compared to time, you can see it goes faster and faster and faster. And then over here on the right-hand side, we just have what it looks like for different values of R, right? So when we have this positive value of R, super fast population growth rate. You can have negative values of R, which means you have a trajectory of decline, a fast decline, right? So again, this graphic on the right is just showing you what the curve, the exponential curve looks like when your R values are different, okay? So on that graph, we have trajectories for exponential population growth. They all start from a population size of 100 just to have a starting point, and then sort of different values of R and what that looks like. Okay. Looks like there's a bunch more in the chat. Oh, there's still lockdown stuff going on in the chat. Okay. Okay. Okay, so here's an example of like a real world example of exponential. So this is for reindeer. These reindeer were, the reindeer here herd on St. Paul Island in Alaska was introduced in 1910. So there's some old data. So there's this reintroduction program, and these reindeer were released there. At the time of the reintroduction, the population had 4 males and 22 females. In only 30 years, the population exploded, increased to 2,000 deer. So this is very much an exponential shape to this curve, right? It gets bigger and bigger and bigger. And then right here, well, they were on an island. And then obviously an island is a finite area, which means it's going to have finite resources. And so they basically grew so large, they depleted all the resources on the island. And then they crashed. And the crash was exponential as well. So this large crash. So this is the type of curve that's pretty typical of populations that grow rapidly and then exceed resources. And this is going to become important when we talk about logistic growth in the next lecture. But this is a sort of classic exponential growth, but then resources exploited, overexploited, none left, and the population crashes. So here's another example of exponential population growth in a more really cool way, I think. So this is a second example of exponential population growth, but this has to do with recovery of an endangered species, the whooping crane. So I posted, I hope I remember to post the paper by Cannon from 1996 on D2L. So whooping cranes are North America's largest bird, and they're a longtime symbol of America's conservation movement. So they were sort of a poster child for conservation. They're native to North America, and their current population is estimated to be at about 700 birds. But in 1942, the entire population had crashed to only 22 birds. There were only 22 birds left. And that decline, you might not be surprised, was primarily due to human actions like overhunting and development of the shorelines and the farmland into farmland that then, of course, led to habitat loss. But what's really cool is through a really active captive breeding program and reintroduction program, the species has recovered. So the data I'm showing here, these are the data, I took the data out of the publication. The data are listed in table 1, and I plotted them in Excel just to see what it would look like. And so I made this figure from the original data in table 1. And these data are based on counts of adult whooping cranes annually at the wintering grounds in Texas where they go. And so if you, the black dots are the real data and then just connected with a line. But then the red line is the fitted line that I used, the trend line that I applied to the data. And it's very much an exponential trend line, which is great news because here's an animal that we're trying to recover. So having an exponential population growth in this case is what was desired, right? And so in March of 2019, so a year and a half ago, was a really significant milestone in the recovery of this animal, the conservation of the whooping crane, because one of the main breeding centers was in the U.S. at the Patuxent Wildlife Center. So it's a USGS, United States Geological Survey research site, which is the Patuxent Wildlife Research Center. In March of last year, they transferred the last 2 cranes from their program. They had about 75 individuals in their flock that they were rearing there. And so basically they transferred the last 2 and then they closed their captive breeding program. Like after 50 years, it was such a great success that they were able to close the program. So that captive program began in 1967. And the way they started the program was the U.S. Fish and Wildlife Service captured a young whooping crane, one young whooping crane, and then collected 12 eggs from the wild here in Canada, and then brought them to the Patuxent Center and started the breeding program. And so the overall conservation goal for the species was to establish new populations in places where they used to once live. And then the effort at Patuxent Wildlife Center became one of the world's largest captive breeding programs for the species and a model basically for science-based reintroduction of endangered species. So it's a really lovely good news story. I mean, the paper that I posted for you is from back in 1996. So the program had been going on for some time, but it's really nice to know that as of 2019, they were able to say, we succeeded and be done, which it's so great to hear those positive stories too. Okay, so we can consider how the growth of rate of the population changes as population size changes. So this value, so this dn over dt, right, the change in population size with respect to time, this relationship, when you plot it against population size, it's a linear relationship, right? It's a straight line with the slope of that line is r, that per capita growth rate. Okay, so if you remember what the equation is for a straight line, it's y equals mx plus b, right? And m, that's the slope. So in our case, m is r. It's this value, it's the slope of this line, right? Y is the y value, that's dn over dt. And x is the x value, which is n, right? And b is the intercept in this case. Right? In our case, the intercept b is 0, right? So the value is 0 for there. Okay, so if you actually write that out, right? So remembering dn over dt, right, we said is equal to Rn, right? And if we apply this y equals mx plus b formula, so y is this dn over dt, right? And we said that r is the slope, so that's your m times your x. And then the plus b part, in our case, the b, this intercept, it's 0. So basically, this is plus 0, right? Which means we can just cancel it out. So then we get to that equation that we just talked about, dn over dt is equal to Rn, okay? So that we get to that. So we can look at it in terms of this equation for a straight line. Again, the plus b part, b is 0, so then that just removes that part from the equation. So we can look at this in terms of this describing the slope of the line, okay? So we're going to be comparing the relationship of this per capita growth rate, this little r, to population size across the different models. So when we talk about logistic next time, we'll do a comparison between the two so we can see how they all compare, right? So since the r is a constant value, remember it's the definition of exponential is that r is constant. There's a single value for r, right? So if you plot that, the value of dn over ndt versus population size, r is just a flat line because it's a single value. So what's happening on the right-hand side of this PowerPoint slide here is just this again with some more colorful interpretations, but the same idea, right? So the slope of this line is r, the per capita growth rate, and then when you plot that as the dn over ndt against population size, it's a flat line because that value of r is just a single value when you're talking about exponential. Okay, so typically exponential growth doesn't occur in the long term, right? Like we saw with that reindeer population in Alaska, on the island of Alaska. Humans, might be the one species for which this exponential model seems to keep happening, but I mean, we can talk about actually the global pandemic. Disease is one of the things that causes populations to be knocked back when they hit carrying capacity. So there's a sort of a frightening thought that perhaps the COVID pandemic is showing us that we can't continue this exponential population growth trajectory that we're on. Exponential growth does occur in the short term. However, we can see that happening. So, when a population first establishes in a vacant suitable area, so back to that metapopulation idea, when a dene goes extinct and the patch is available for recolonization, initially the recolonization could have an exponential population growth trajectory until it reaches carrying capacity, which is what we're going to talk about next time when we talk about logistic. Okay? So the population when it initially establishes, can grow according to exponential growth, and of course, until it uses up the resources. So to use the model, the exponential model for predicting short-term changes in populations, we need to use it in a different form than the one that I showed you. The dn over dt equals Rn, that formula that's the y equals mx plus b version of the formula. You can't do much with that. We have to change it into a mathematical formula that's actually usable to make some projections about populations. And so the way we do this is to apply calculus. And in this case, I'm not going to get you to do the calculus, but the way we do it is to apply calculus, and we do some integration of that dn over dt value equation. And the end result is when we do it, we get this. Nt equals no times e to the rt. Okay, so when you do the calculus on dn over dt equals Rn, this is what you get in the end. Okay, so this is the exponential growth equation. So nt is population size at time t, and 0 is the initial population size, right? E is the base of the natural logarithm, which and r is that per capita growth rate, and t is time. Okay, so we have this superscript of r times t here. Okay, again, that r is that instantaneous population growth rate. Okay, and so we can use this equation to figure out what that value of r is. Remember, in exponential, the r is constant, right? So we could figure out what that r is if we went out into a population and we took some census data in 2 different time frames, right? So if we went out and got an initial census of how many animals were there, and then over some time period went back and did a second census, we could use that information then, because we know the initial size, the new size, and the time that passed between those two censuses. And then we could solve for R and figure out what the per capita rate is. So we're going to do a hypothetical example of that using the equation, talking about these cute little meadow voles who even have little ear tags. So we have this hypothetical population of meadow voles, and we're going to do two censuses, and we're going to ask the question, what is the per capita growth rate for these little dudes in a newly colonized area? So when we go out and do our first census, and we capture 6 of these little guys, okay? And then 10 years later, T is 10. 10 years later, we go back and we survey again. So when we do our second survey, we get 250 individuals. So 10 years later, so you could actually subscript this with the 10, right? We go back 10 years later, and now we have 250 individuals, okay? So we want to figure out what is the value of R. What is that per capita growth rate for this population, okay? And so we can figure it out by applying the formula, okay? I can do this, and I'm using my screen rotated in a different direction than normal. So it's kind of funny because I move left and everything goes to the right so that this isn't backwards for you guys to see. Okay, so I'm going to erase this because I can keep it up higher. So hopefully you've got that written down. So this is our example. Again, we go out for the first survey and we collect 6 of these guys. 10 years later, we go back and we collect 250 of them. So now we want to know what's the value of little r. So we're going to solve for little r. So we're going to substitute into the equation, right, that nt equals no e to the rt. So what we've got is 250, right, is going to be equal to 6e to the r. We don't know what r is. That's what we're trying to solve. And we know that t is 10, right? So we've got r times 10, okay? So the first thing we can do, we've got some whole numbers on both sides. So we can divide both sides of the equation by 6, right? To get rid of the 6 that's on this side, right? So when we do that, I'll just jump to the division. So it ends up being 41.7 is now equal to, I'm going to do 10r there, okay? I just switched it around, okay? So we just divided both sides of the equation by 6 so that we only have a number down at the baseline on this side. Okay, now, if you remember some of your original mathematical stuff that you've learned, we have to get rid of this base of the natural logarithm and get this superscript down to be at the base layer. And if you remember, the way we do that is that if you take the natural log of this, it gets rid of that e and brings the 10r down to the base level, right? So if you remember that, I hope you remember that. That's just a memorization thing, right? Because again, e is the base of the natural log. So if we want to get this superscript down to base level, we take the natural log. So, and remember with your math, you have to do what you do to one side of an equation, you always have to do the other side. So now we get to the point where we have the natural log of 41.7 on this side is now equal to 10r, right? So we took the natural log of both sides. Okay. And then when you take the natural log of 41.7, which I have already calculated, it is 3.73. Okay, 3.73 is equal to 10r. Okay, now what we're trying to solve is r, right? So we got to isolate that r. So the way we isolate r, then, you have to do to both sides of the equation, right? We can divide both sides of the equation by 10. So we're going to have 3.73 divided by 10 is equal to r, right? So 3.73 divided by 10 equals r. And then when you solve that, it equals 0.373. So we have calculated the per capita growth rate for these cute little meadow voles is 0.373. Okay, so we figured that out by substituting in. So again, we applied the equation that's on your screen. to 2 surveys worth of data that were 10 years apart. And that allowed us to figure out the per capita growth rate, which is 0.373. Hopefully that makes sense. Hopefully that's the little chalkboard thing's working out. I thank my daughter, I stole it off her bedroom wall. Okay. Okay, so I have another practice problem, and I've actually posted additional study questions on D2L for you to work on in preparation for the midterm exam. I see a flashing chat, so I'm just going to check to see what that says. What button on the calculator do you use for natural? Oh, and by the way, so that means you're allowed to have a calculator for your, you're allowed to have a calculator for your exam. Okay. Let's do this example. So it's similar to the elk one, the reindeer one. So you have 6 elk. There's 3 males and 3 females that are introduced to an island where there's currently no other elk. The habitat is great. The resources are excellent. And the population grows at an instantaneous per capita rate of 0.3. R equals 0.3 per year. If the elk population on the island reaches 500, the elk will deplete the resources and start to go extinct. Okay, so 500 is the cutoff. So if you think about that reindeer example, it was 2,000, right? And then they started tanking. So if the elk population keeps growing at that same per capita rate, that R value of 0.3, how many years will it take for the population to start on that trajectory for extinction? So in this question now, it's asking you to solve for T, right? In the last question, we solved for R. This time we're given R. And it tells us that R is a single value here. So we know this is an exponential equation, an exponential application, because it's giving us a constant R value. Okay. All right. So we can figure this out and solve for how many years is it going to take for this elk population to start crashing, right? So we're going to use the formula again of NT equals NO e to the RT. So let's just recap that formula. Okay. NO equals NT equals NO e to the RT. It's very small. Hopefully you can see that. Okay. So in this example, our N equals 0 is 6, right? We've got 3 males and 3 females. So there's 6 at the start. We know that our R value is 0.3, right? We know that our NT value, the second census data point, is 500. So in this case, it's when the population is going to start to crash at 500. So what we're trying to solve for is that T value. How many years is it going to take for that to start happening? Okay. So again, we're going to use this equation and substitute in the values and solve for what T is. Okay. So we've got 500, right, is equal to 6 times e to the 0.3 T, right? So that's what we end up with. And so again, we want to get all the full numbers to be together. We're going to divide both sides of the equation by 6. So you're going to have 500 divided by 6 is equal to e to the 0.3 T, right? So divide both sides by 6 and you get 83.3 is equal to e to the 0.3 T, right? Again, I just divided both sides by 6. Get rid of that thing. Now, if you remember, we need to get rid of this e, right? So we need to get the 0.3 T down to the base layer. So again, we take the natural logarithm, right? We take the natural log. So we have to take the natural log of both sides because you always have to do the same thing to both sides. So we take the natural log of 83.3, and now that's equal to 0.3 T, right? Again, so on your calculator, you would hit the natural log, the ln for natural log. Okay. The natural log of 83.3 is 4.42. It's 4.42 equals 0.3 T. So of course, now to solve for T, we have to divide both sides of the equation by 0.3, right? We have to do to both sides of the equation. So 4.42 divided by 0.3 will be equal to T. So you do that, that division to isolate what T is, and you'll get 14.9 14.7. So it will take 14.7 years for the elk population to deplete all its resources and start to go extinct. Okay, so that's how much time it will take. So I recommend when you're doing answers to these questions that you take the time to actually write out all these pieces. What is your NO value? What is your R value? What's your NT value? And then putting all the pieces into the equation and doing the steps to show the calculation, so that if you do make a mistake, I can still see the steps you've taken to see if you at least have made the right steps, but maybe just wrote a number down wrong or something. So you can get partial marks by showing the details of your steps. Okay, so don't just write an answer down, show the steps about how you get there. Okay, so that's two examples of how the exponential growth equation can be applied. It can be applied to figure out R, or it can be applied to figure out T, and it can be applied to figure out the N values as well, right? So there's different applications that you can use now that we've got it into this formula that allows us to do something with the data. Okay, it's a bad idea.
Are three significant figures typical?
That's a really good question, actually, Cheyenne. That's probably more significant digits than you need. I mean, the data I put here is only one significant digit, right? When I included the equation here, or the R value here, it's only 0.3. But I mean, 2 decimal places is definitely sufficient. That's a good question. Okay. Any other questions as we're thinking about that just then? Anybody? It's definitely like
you said that we if write out our equation is better, but since we're doing this online, right? I'm not quite sure if the setup allows us to do like a what's it called? Like, you know how we do a superscript and a subscript? Yeah. So like putting just N0, does that work too? Like, would you understand that?
Yeah. So that's such a good question, Antonia, because I've made the exam and I've inputted it into D2L, and I actually put in the instructions. You won't be able to probably do subscripts, but just use annotation that it's going to be pretty obvious to me what you mean. So for example, if you're doing, the capital R subscript 0, maybe you'll put capital R and then just a lowercase o, right? So it's really hard to do this kind of an exam that involves math on D2L without it being just excessively time consuming to pick, because you can put mathematical formulas and stuff, but I don't want you guys to waste time with that. So so that's such a good question. So I just want you to use annotation that at least it'll be pretty straightforward to me what you're trying to do. So for division, you just use the backslash and stuff like that. I think I just saw a chat come again. Let me just have a look. Yes, so Brooke has a good one in there too. So if you were trying to say superscript, you put E and then you put the hat, right? The little hat symbol that means upscript, right? And then asterisk means multiplication. Absolutely. So use annotation so it'll be pretty obvious to me what you're trying to tell me. Okay.
Okay, thank you.
Yeah, it's tricky. I mean, there are so many reasons why I wish we were all together doing this in person. and if you could write the exam with your hand instead of typing it would be so great. Anyway, we're going to try to work our best on all of that, and I'm going to try to understand what you're telling me, but make it as easy for me as possible to interpret what you're doing. Okay. All right. Now we'll go to the next concept, which is called doubling time. So knowing the value of little r for population, that per capita growth rate, it also allows us to calculate something that's called doubling time of that population growth. And this might be important, if from like a population management perspective, if you want to know when your population that you're introducing doubles in size, because maybe that's your recovery target for that species. Or maybe like on the flip side, maybe it's some horrible invasive thing and you're trying to manage that outbreak. And so you want to know when the doubling time is, basically how much time you have to get to that doubling time sort of thing. So there's some value for calculating doubling time. And so the doubling time occurs when, so doubling time It occurs at the time when population size at time t divided by population size initially is 2, right? The population is 2 times bigger, doubling time. So what you're trying to figure out is what this t value is. What time into the future does it happen that the population size at time t divided by the initial population size is 2, twice as much, right? So again, this is it could be interesting from a conservation or recovery perspective, but it might be interesting from like sort of an outbreak management perspective as well. Okay, so the doubling time occurs again when this nt over no is equal to 2. And so if you rearrange, so we'll go back to my little blackboard here. Okay, so if you go back to the equation, nt equals no e to the rt, right? We go back to our equation. And if we rearrange that equation by dividing both sides by n0, so we're going to divide both sides by n0, right? So you get that nt over no is equal to e to the rt, okay? If you rearrange both sides. Okay. And now you substitute. So I just said on the screen there that nt over no equals 2, right? So now we can substitute in, because we've just said that nt over no is equal to 2, right? So now we have 2 equals e to the rt, right? Right? We just did a substitution because what it says on your computer screen there is nt over no equals 2. Okay, so we just substituted that 2 in. Right, and again, so now we want to get rid of this e with a superscript. We want to get it to the base level, so it's going to be taking the natural log, right? So we got to take the natural log. So the natural log of 2 is equal to RT, right? Natural log of 2 is equal to RT. And the natural log of 2 happens to be 0.693 equals RT, right? Just so the natural log of 2 is 0.693. And then we're trying to isolate t, right? We're trying to isolate the time, the doubling time. So then you would divide both sides of the equation by r. And when you divide both sides of the equation by r, which is what's shown there on the screen, you get t equals 0.693 divided by r. So that's when the doubling time happens. Okay, so if we then apply that, so much of what I've just written here on the chalkboard is actually on your screen for you already. Okay, but now let's just quickly apply that to our ELK data, for example. So if you remember, so from the ELK practice problem that we just did, right, the R value in that ELK problem was 0.3, right? That was the information that I gave you. So if we figure out t is equal to 0.693 over r, our R value is 0.3, right? So 0.693 divided by 0.3. When we calculate that, we find out that the answer is 2.31. So that means that for that ELK population, the doubling time is about 2.31 years. So we did that equation based on that calculation based on years as the time, right? So again, for that ELK practice problem, the R value that was given in the question was 0.3. So then you substitute in t is equal to 0.693 divided by that 0.3. And when you do that simple math, the t value comes out to be 2.31 years. So that means the doubling time for that population is about 2.31 years. Okay. Okay. We can also estimate R in another way based on a larger number of samples. So if you do multiple censuses over time. So again, if you consider the formula, right, this is our exponential formula, nt equals no e to the rt, right? If we take the natural log of both sides, so natural log of both sides, and then solve it out. So natural log of nt equals the natural log of no plus the natural log of e to the rt. And so you should know by now that when you take the natural log of of e to the superscript, it gets rid of that and brings the superscript down to the base level. So now you have the natural log of nt is equal to the natural log of no plus rt. And again, that gets us back to that slope of a straight line, y equals mx plus b. Now I've got it written just sort of reversed here, but it's the same idea, right? So y is the natural log of nt, right there. X is time, right? X is time. And the slope of the line is r, right? Right here. Slope of the line is r. And the intercept, b, is right here, the natural log of that NO. So it all fits again to make the slope of a straight line. So if, again, you can figure out what r is by doing multiple censuses, right? And then making this plot, and then you can figure out what r is by knowing the equation for that line, y equals mx plus b. So you can figure out what the slope is by solving the equation of the line. Okay, so this is what we predict for exponential growth. So if we take population censuses at several different times and then plot the natural log of population size over time versus time on the x-axis, we can predict that if the population is growing exponentially, then the points should fall on a straight line. Remember, because the definition of exponential is that r is a constant single value. So if we do this natural log transformation and plot those values, it should fall on a straight line. And from that, we should be able to figure out what the r value is. So that's, if it works, if we take the natural log and plot it and get a straight line, that's more indication that that population is really growing exponentially. Okay, so again, applying this equation of this y equals mx plus b, and again, I just have them reversed here, y equals b plus mx, but the same thing. We can figure out what the per capita growth rate is for that. So I did this. I took the whooping crane data that I already showed you, pulled out of table 1 from the paper, and I tried plotting it. I tried doing a natural log transformation to see what would happen. And it's pretty cool because it works. So the black dots are the real data that I did the natural log transformation for. And then in Excel, I applied a trend line. I applied a linear trend line, and it actually fits really well. It's a really nice straight line, and it's a good fit. The r squared value, which tells you about the fit of the data of the line, is 91%. So 91% of the variation in those data points is explained by that straight line. So that's a really good fit for that straight line to the data. And so then Excel, it's pretty easy. You tell it a trend line, then you tell Excel, tell me the r squared value and tell me the equation for that line. And of course, when it tells you the equation for the line, you can then get the value of the slope. So here it is, y equals mx plus b. And so here's that m value, and it is therefore can be interpreted that the per capita growth rate is 0.037. It's a very shallow slope, but there you have it. So I would say that these whooping cranes are growing in an exponential fashion, because when I natural log transform the census data and apply a linear line, it's really a great fit, and we can then get this per capita growth rate calculation from that. Okay. Hopefully that makes sense. Okay. So that's all the stuff I wanted to cover today. Here's a bit of a summary of the things we went over, talking about geometric and exponential population growth. Okay, we compared these finite models versus instantaneous models, and we're mostly talking about the instantaneous ones. So we first mentioned geometric population growth, which is shown here, the equation. We didn't do any calculations with it, and you don't need to do any calculations with it. I'm not going to ask you anything about geometric population growth calculations. I will, however, ask you about exponential population growth to solve that, and which is why I posted the extra study questions on D2L. So you should work on those as you study for the midterm, and I will post the answers to those study questions on D2L, but I will not post all of the details about how to get to them. I'll just put the final answer so that you can work through it and keep trying it until you get the answer. Okay. So the important thing here is this equation is the one you need to use for exponential. population size at time t is equal to initial population size times the base of the natural logarithm to the power of the per capita growth rate times time. So again, key thing about these exponential growth models is that birth rates and death rates remain constant, okay? They don't change over time. The R, the per capita growth rate, therefore is constant, right? So that's by definition. If we say birth and death rates don't change, then that means the R value also does not change. And so you need to know how to solve problems using that, as I already said. So similar to the examples that we just did now together in lecture, and what you're going to do hopefully do for your study questions. And then the last thing we did was calculate this doubling time, which again can be useful in a conservation context, in a management context. Okay. All right. So I will stop sharing then, and then maybe now we can talk a little bit more, if you want, about exam stuff. How many people are here? 54 people are here. Okay, so did you guys figure out the lockdown? It looks like you must have figured out lockdown. Okay, it looks like you did. All right. Are there any more questions? Were you able to see the little chalkboard thing as I did stuff? I hope. I have chalk dust all over me now. Hopefully that worked.
We saw it.
Okay, great. Thanks, Cameron. Any other questions? Like I said, we have another lecture on Monday, and that lecture is on logistic growth, and it will be included on the exam. You'll have the 3.5 extra days to study, 3 days to study until the exam for that content. But as I've said before, this should be somewhat of a review. You should have covered this a little bit, at least in principles of ecology, maybe not to the same depth that we're doing it here with actually doing some calculations. Any other questions?
I just had a question about the life tables that we looked at last lecture.
Yeah.
So for the NX value, that value is not calculated, right? Like that's field data?
Right. So
Okay.
the N values and the M values are the data that are collected in the field. Those are like the go out and sample. How many animals are still there in each cohort if you're doing a cohort life table in each age class? Absolutely. And same with the M values. How many female young are produced per female? Those M values, you have to go out and collect those data. The rest are all calculated. That's right. So survivorship is calculated. The mortality rates are calculated. The killing power is calculated. Don't worry about the killing power. As I said last time, it's an interesting metric, but it's not always shown in life tables. So I'm not so worried about you guys knowing that one. But I do want you to know about survivorship and mortality calculations, and then how to use those data to get at that capital R sub zero calculation and generation times as well.
Sorry if you already went over it and I just missed it. But what is the format for the midterm going to be? Is it going to be like multiple choice, short answer? I know we're going to have calculations.
Yeah, no. Thanks, Samantha. I did not actually mention that. So the way I have it set up, so I did write the exam and I have put it into D2L, and I'm going to hopefully do a test run with somebody on it later today at 1 o'clock to make sure it works okay. It's a combination of things. So there's some short answer, like 2-point, definitions explain type things, 2 pointers. And there are true false, which are 1 point each. And then there are short answer questions, shortish answer, like medium. I guess they're 10 points each, 12 points each, 10 or 12 points each. And then there's a long answer question. And I'm sure you can already guess what that long answer question is going to be. And one of the things that's not going to be present on the test is a choice. You have to answer everything that's there. When I do these exams in person, I try to make some choice. On D2L, it's not quite as easy to do that because for a few reasons, but in any event, there won't be choice. You have to answer everything that's there.
Okay, thank you.
You're welcome, Samantha. There's a private question. Is it possible to post a practice quiz with the lockdown browser? I don't think I can do that, but hopefully by now, with the stuff that's been going on in the chat, I'm hoping that you all can figure out the lockdown thing. If you have trouble with it, I can connect with Melanie Smith, is one of the technologists in the department who helped me last year to do the animal histology exam on D2L. And so if there are problems with lockdown, let me know and I will connect you with Melanie because she knows D2L really well. I've taken a bunch of workshops on it, but I am still learning some of the pieces of how it works. So if you do run into trouble with lockdown, let me know. Hopefully that link that Luis has posted there in the chat will work for everybody. Any other questions? We have a couple minutes left if anybody wants to ask anything else. It is unfortunate that we have to do online tests. And then, of course, maybe you guys saw the email as well from the university. I guess it was Tuesday was the university Senate meeting when they decided that courses next semester will also be online. So the January courses will also be all online. For any possibility of doing things in person, there's a process of application. But one of the main concerns at the university is that a lot of you students are not actually here in Sudbury. So if we try to do any in-person stuff, it's not fair because some people are not here and we can't ask students to commute to campus from Toronto or wherever you might live, right? Some people even live overseas who are attending classes or in more remote communities up north. So it's unfair and the university doesn't want us to put a burden on students for having people have to come to campus to do a lab. So you will find, unfortunately, that next semester there's very unlikely there will be anything in person, which is really unfortunate, but of course we need to remain safe.
I have a question about the formula. So I'm assuming for most of them, we'll use the original exponential growth formula. But if we're doing the doubling time, do you want us to actually use that formula to then get to doubling time, or we can just use the doubling time formula?
I think I don't quite understand your question, Brooke.
So in the lecture, we went over how to use the original formula to then find the doubling time formula. So do you want us to go through that process? Okay.
No. Okay, now I understand. No, you do not need to know how to derive that formula. You just need to know how to use it.
Okay, thank you.
Yeah. That's a good question, Brooke. Yeah, because some of the time with some of the stuff we're going to do later in the course, you will actually have to derive how we get to some things. But for that, you don't need to.
Thank you.
Anybody else? No? Okay, if there are no more questions, of course, you're free to go. See you all on Monday. Well, I wish I could see you all on Monday.
Thanks, Jackie.
Welcome.
Dr. Litskis? Sorry, someone asks in the chat, how does lockdown browser work?
Oh, and Mitchell says, yeah, I've never used it. So the way it works is that it prevents you from going anywhere else on your computer or your tablet, whatever you're using. You're only within the test in D2L writing the quiz. So you can't access the hard drive or the internet on your computer to go search for answers. It's a way to prevent people from cheating. It's not perfect, right? Because you can, of course, have your notes in front of you and stuff. But as I said at the start, my hope is that I can trust you all to be honest and use what you've learned and try to apply that knowledge to the test. But it is what it is. Okay. All right. Anybody else?
I have a quick question.
Yeah.
Sorry, my brain is jumbled. How many questions should we expect? Is it a particularly long exam? I've had a few midterms and I'm like, oh my God.
Yeah, no, I hear you. So the length of the test, the length of the midterm exam is the same as what it would be if you guys were doing it in person. So I've made it the same length. In terms of points, it's 90 points. It's 90 marks. So I'm asking you for 90 tidbits of information. And when I have had the exam that long of 90 points in the past, some people have been able to complete the test in like 45 minutes, and other people take the full hour and 20 minutes. So it should be, if you know your stuff, it'll be totally doable. You'll be able to plow through it really quickly. If there's some stuff you're unsure of course, you'll have to think a bit more. And I think for a lot of people, actually typing their answers is faster than handwriting anymore. So it might actually be faster because it's just on D2L, it's just a free form box where you just type in your answer. So it might actually be, like I said, a bit quicker because handwriting is slower for a lot of people. But that's a good question, Kiana, and it should be, it should not be longer than normal. Like I've based it on the same amount of points that I've done for the midterm when we do it in person. I hope that makes answer. Good.
It does. Thank you very much. And I had one last question. When we're writing, because there are a few like short answer questions or longer answer questions, are you looking for point form, paragraph, like well formed?
No. So I mean, I do want you to use correct spelling, and because you're typing it, it's actually going to help with spelling as well. But bulleted lists or sort of comparative, columns of stuff. I don't know if you can even do that on D2L, but bulleted lists are totally fine. I don't want stream of consciousness writing that I can't understand, but I'm not really worried about full sentence structure and stuff like that in this case. If there is because there's no questions on this exam that are like, craft an essay about this particular thing. There's no questions like that. That's not to say that on the final exam, I might have you write something a little bit more precise, but the easier you can make it for me to mark it, the better.
Perfect. Okay, sweet. Thank you so much.
Welcome.
Also, sorry, I have a million questions.
No,
This is the last one. For some of the equations that we've been doing this class and the last, those are going to be on the exam, correct?
Yeah.
Okay. Okay. I'm struggling a little bit with them. I'm going to take the weekend to just like cruise through it and see if I can get myself on track. Are there any outsources, or is there anything that that I could particularly like YouTube or Google just to get a bit ahead? I do really well when it's explained to me a million different ways. So I use YouTube a lot. I just want to make sure I don't Google something that's like similar, but just different enough that it'll make it wrong.
Yeah. So I think I would recommend not Googling stuff because I think that'll get overwhelming. So what I recommend actually, Kiana, for the life table, for example, is to actually take either the cohort life table that I gave you for the sparrows or the hypothetical life table that I posted, and actually just sort of erase the cells, like, empty the cells of the data except for the ones that you need. So the X value, the N value, and the M value, and just practice the calculations. Practice doing the LX values, those survivorships, practice doing the DX values and the QX values, and just run through them. I mean, those mathematical formulas are actually pretty straightforward. They're just additions or division kind of thing. And so that's what I recommend. The best way to do it is to dive into our lecture content rather than trying to add more from outside, because it's a rabbit hole. You could just like dive down into like everybody else's version of those lectures. And I think that would become overwhelming. So I don't recommend that. But I definitely recommend like just try running through and make sure you get the same numbers that I got in the slides.
Okay, sweet. Thank you very much.
You're welcome.
Those are all my questions.
Well, if you have more, that's totally fine. I'll be here for another few minutes if you need to ask questions.
Thank you, Doctor. Have a good day.
You too, Kiana. Anybody else? There's still a couple people on. Anybody else? Johnny, are you there? We had trouble with you at the lab. Johnny, can you put on your microphone for a sec? It'd be good to ask you about what happened in the lab. trouble. Johnny Lamb, are you there? You turn on your mic. All right. Looks like there's no more questions. So I'm going to go. So have a good weekend, everybody.